Okay, so we are revising chemistry test 2. Okay, so in this video, we are going to revise section A, and then in another video, we'll revise section B. Okay, so let's go to the questions. So we have 50 questions in this section A. Okay, and then the first question here, they're saying fructose is the sweetest sugar known in biochemistry. Surprisingly, okay, glucose is not as sweet as fructose, and yet these two sugars are said to be related. Okay, and then the question now is state the structural relationship of these two sugars. Okay, so what's the structural relationship between these two sugars? What do you think? Are they anomers? Are they apimers? Are they functional group isomerism, or there is no relationship? What's the structural relationship between these two? No. Okay, anyway, I'll answer. Okay, so the structural relationship between fructose, where is the fructose? Okay, between this glucose here and this fructose here. Okay, the relationship there is just the functional group. Okay, so in glucose, you have an aldose. Okay, you have an aldehyde group there as the functional group. And then in this fructose there, we have a ketone. Okay, we have a ketone group there. So this fructose is called a ketose. And then this glucose here is called a what? An aldose. Because it has an aldehyde group, this is a ketose because it has a ketone group. Okay, so the functional group there differs. So that's the relationship. Okay, so the relationship is functional group what? Isomerism. So C here was the best answer. Okay, and then number 2, they're saying what is the meaning of the word isomers as it is used in organic chemistry and biochemistry? Okay, so what do you think is the answer here? Isomers, those structures that are having different structures, or they're having the same structures, or have structures that have equal parts, or structures that have different parts. Okay, so you have to know that isomers have the same molecular formula. Okay, they have the same molecular formula. Okay, let us continue. So I was saying these isomers, okay, they're just isomers have the same molecular formula, but they have different what? Structures. Okay, so it means what? It means what? Okay, they don't have different parts. Okay, so get this correct. They don't have different parts. They have the same molecular formula. Okay, so the parts that they have are the same. But what is different is they have different structures. Okay, so isomers as used in organic chemistry can be what? The best answer here is C. Okay, the structure is having equal parts. Okay, so the structure has equal parts. That would be the cardinal definition. And then those equal parts that it has, they can be arranged differently. Okay, yeah. So the most correct answer here, we can pick C. Okay, so I'll only stop when you ask questions, you guys. So question 3 here, they're saying, can epimers be considered as non-identical structural twins in biochemistry? Okay, the answer is yes. Okay, the answer is yes there. So why? we're saying epimers differ at only one stereocenter. Okay, they are structurally similar, but are not identical. Okay, their structures are similar, but they are not identical. So we can call them non-identical what? Twins. Okay, as this this phrase that they used here. Okay, so can they be considered as non-identical structural twins? Yes, because why? The structures are similar, but they are not identical. Okay, how are they not identical? Because they only differ at one stereocenter. Okay, that's what epimers are. So here the answer we say yes. Okay, and then question number 4, they're saying on the basis of structure. Okay, so the most important word here is on the basis of structure. This basis of structure. What amino acid? Okay, so you just look at the structure of the amino acid, and then you pick out what it contains. We know that the structure of the amino acid, okay, on one end it will have NH2, okay, and then here they can be anything, and then on the other end it will have what? COH. Okay, so the best way to describe the structure of this amino acid is to make sure that you include this group and this group. Okay, so this group here is known as the amino group, right? Okay, and then this group here is known as the carboxyl what group. So when you come on your answers here, they are saying on the basis of structure, what are amino acids? Definitely they are not building blocks, because this one here doesn't tell us anything about the structure. Okay, we can't say they are body nutrients. It doesn't tell us anything about the structure. And again, we can't say inhibitors of receptors. No, it doesn't tell us anything about structure. The only thing that tells us anything about structure here is this one. So we say that amino acids are carboxy metherium what derivatives of ammonia. Okay, they're carboxy metherium derivatives of what? Ammonia. Okay, so the correct answer here is C. So you can see that in this definition here, this carboxyl here gives us some news about this carboxylic group, right? Okay, so the answer there is B. And then number 5, they're saying in organic chemistry and biochemistry, what are diastereomers? Okay, what are diastereomers? So diastereomers are just non-mirror images of each other. Okay, so they are not identical. If you put them in the mirror, they will appear differently. Okay, so diastereomers are stereoisomers that are not mirror images. Okay, they differ in the arrangement of atoms. When you arrange them in a 3D space, they are going to differ. Okay, so these diastereomers are not the same as enantiomers. Okay, when you talk about enantiomers, you talk about something else. Okay, right. So the best answer here is that they are non-mirror images. So pick A. And then number C, 6, they're saying state the number of the types of constitutional isomerism we have learned in biochemistry. Okay, so I don't know you guys, how many did you learn? Okay, but in general, we have 3 of them. Okay, so the number or the types of constitutional isomerism we have learned in biochemistry, generally there are 3. Okay, so the main 3 types of structure isomerism, because when they say constitutional here, okay, structure. So the main 3 types of structural isomerism are 1, constitutional isomerisms, okay, and then we have positional isomerisms, and then we have functional group isomerism. Okay, so the constitutional what did I say? Okay, I said positional. Yes, positional is one of the constitutional isomer. And then the other one is functional group, and then the other one should be chain. I made a mistake. I mentioned constitutional again there. Okay, so the 3 types is the chain, the position, and then the functional group. So these are the 3. main types of structural isomerism in what? In biochemistry or in chemistry. All right. So the correct answer is 3. Okay, and then let's look at question number 7. So question number 7, they're saying basing on structure and atomical composition, what are carbohydrates? Okay, so we want strictly the definition to what? Show the atoms that carbohydrates contain and maybe the structure. Okay, so basing on structure and atomic composition, what are carbohydrates? Okay, so someone might say, okay, someone might say compounds containing carbon, hydrogen, and oxygen. Okay, so this one here, this definition here, only tells us the atomic composition. It doesn't have anything about structure. Okay, so it cannot be the correct answer here because it only tells us about the atomic. Okay, and then compounds having sweet taste. Okay, it doesn't tell us anything about the composition, even the atomic. And then on C here, they're saying compounds with high nutritional value. It's the same with this answer. It doesn't tell us anything about the structural aspect or the atomic aspect. Okay, but when you go on D there, okay, they're saying they're derivatives of hydrated carbon. Okay, derivatives of hydrated carbon. So that means what? Okay, that means hydrated carbons are compounds that you can write in this form. Okay. Okay, so hydrated carbons are carbohydrate carbons that you can write in this form. You have CN, and then I'm pretty sure here you have water like this. Okay, and then you have M there. Okay, so this is a hydrated carbon because you have water here being added to the carbon. So these carbohydrates, they come from this hydrated carbon. Okay, so you can see that from this hydrated carbon we can have a view of the structure of this because I can see that in its structure this C will be bonded to the H and it will be bonded to the oxygen like that. Okay, and then from that hydrated carbon, I can also see the composition of these carbohydrates. I can see the carbon, the hydrogen, and the what? The oxygen. Okay, so the best answer here is D. They're just derivatives of what? Hydrated carbon, if you talk about the structure and the atomic composition. Okay. Right, and then number 8, they're saying amines have 2 most important reactive characteristics. Okay, provide the 2 characteristics. Okay, so I remember I even taught this when we were doing the tutorial sheet for amines. I'm pretty sure I shared it. Is it yesterday? Yeah, I shared it. Okay, so the most important reactive characteristics of the amines, okay, is that they are basic and they are nucleophilic. Okay, so don't forget those 2. So basic and nucleophilic, you can see here, basic and nucleophilic characteristics. These are the most important characteristics of amines. Okay, so just memorize this. Okay, you can watch the full video on amines. It's there on YouTube and it's there also on. Okay, what about question 9 here? Okay, what about question 9 here? So question 9, they're saying on the basis of their respective titration curves, amino acids exist as hybrids, okay, meaning that they exist as molecules having separately positively and negative charged groups at their what? Isoelectric points. Okay, so the question now is provide the term used in organic chemistry and biochemistry to describe these hybrids. Okay, so what hybrids are we talking about? The hybrids that can exist having separate positive and negative charge groups at their isoelectric point. So meaning it can be one point, it can be one compound like this, okay, but at one point Okay, at one point it will be positively charged, at the other point it will be negatively charged. So what term do we use to describe such compounds? Okay, so the answer here is just deuterium. Okay, because the deuterium can be both positive and what? Negative. Okay. All right, so the answer there is deuterium. And then we look at question 10. Question 10, they're saying two molecules of amino acids can react to form a peptide linkage called a peptide bond. Okay, so when you get two amino acids, they can form a peptide bond, okay? And then they're saying in this case, the reaction is referred to as a condensation reaction, okay? So remember that in a condensation reaction, we have a water molecule that is released, okay? The water molecule is released. Right, and then they're saying on the basis of this reaction, so meaning this same reaction where you get two amino acids and then the water goes, a peptide bond is formed, okay? So on the basis of this reaction, what are the important characteristics, which are also known as chemical properties of these amino acids? Okay, so what are the important characteristics there? Okay, so the important characteristics should be three there, okay, because we're just forming a bond there, a peptide bond, okay? So the important characteristics there is that they should be basic, they should be acidic, and they should be what? Nucleophilic. So the best answer there is just what? A. Okay. All these others here don't, they're not necessarily important for the peptide bonds, okay? Like the boiling points does nothing to do with the bond, okay? So the most important here, okay, are the basic, acidic, and the nucleophilic characteristics. It will be one that will be at play for that peptide bond to be what? To form. Okay. And then question number 11 is on cyanosis. Okay. So they're saying cyanosis is a bluish or pinkish tint to the skin and the mucous membrane. Okay. It may be a sign of hypoxemia, okay, where there are low levels of oxygen in the blood. Okay, this would be confirmed by blood gas analysis, blood gas analysis, okay? At what level of hemoglobin is cyanosis clinically what? Apparent. So at what level of hemoglobin will you be able to accept that, okay, this is cyanosis at the clinic, at what level, okay? So the level is 5 grams per deciliter, okay, or more of an oxygenated blood, okay, or an oxygenated hemoglobin in the capillaries, okay? So if you have 5 grams per deciliter or more of the unoxygenated hemoglobin, then it will cause a problem inside your body, okay? And you may be proud to experience what we call cyanosis, okay? So you have a purplish or bluish skin like that, indicating that you have low levels of what? Oxygen, okay? The oxygen can be there, okay? I mean, not the oxygen, the hemoglobin can be there, but the hemoglobin what? Will be unoxygenated. Why? Because there are low levels of oxygen in the blood, and that will cause cyanosis. So the best answer here is this guy here on A. Okay, and then we look at question 12. Question 12, they're saying which of the following individuals would have a clinical diagnosis of anemia, okay? So for us to know which individual will have anemia, we have to know the definition of anemia, okay? All right, so A, they're saying a pregnant woman with HB concentration of 11 grams per deciliter. Okay, and then B, they're saying a male with HB concentration of 15 deciliter. C, they're saying a young lady with HB concentration of 13 grams per deciliter. Okay, so which one do you think is the best answer here?
I think A is the answer.
Okay. Anyone who has a different view on question 12? Anyone who has a different view on question 12? Okay, so the answer is D. It's not A. Okay, because all these here, they define normal levels of the HB concentration. Okay, at least there are normal levels of HB concentration in those specific individuals that they have mentioned there. So there's no individual here that has a lower level of the HB concentration as they should have. Okay, so the answer there is none of the above, because all these levels seem to be normal. Okay, right, and then 13, they're saying what is meant by the term cooperativity in oxygen binding. Okay, what is meant by the term cooperativity in oxygen binding? Okay, so cooperative binding it's from the word cooperate. Okay, so cooperate, it means you're working together, right? Okay, so in cooperative binding, what happens is that when you have hemoglobin in your red blood cells, okay, if one oxygen molecule binds to that hemoglobin, okay, it will be very easy for other oxygen molecules to also bind to that what? Hemoglobin, because that first oxygen molecule that binds to that hemoglobin will be like attracting more of itself. Okay, so you to bind again to the another oxygen molecule just like that. That's what cooperative binding is. So you come to your answer here, you look for whatever is similar to what I've explained. Okay, so anyway, let's start from A. So A, they're saying binding of one oxygen molecule to hemoglobin makes it easier. Okay, yeah. So the same thing I was explaining. Binding of one oxygen molecule makes it easier for the other oxygen molecules to also what? Bind. So this is cooperative binding. Okay, it's cooperative binding. So if the first oxygen molecule has difficulties in binding to the hemoglobin, it means the other oxygen molecules will also have what? Difficulties. So that will be uncooperative what? Binding. Okay. Right. So here the best answer is A. And then we go to question 14. Okay. So question 14, they're saying which of the following would decrease oxygen's affinity for hemoglobin? Okay. Which one would decrease oxygen's affinity for hemoglobin? Okay, they're saying what here? Which of the following would decrease? Okay, would decrease oxygen affinity for hemoglobin. So what do you think here? Which one would decrease the oxygen's affinity for hemoglobin?
The answer is B. High
Okay,
levels of carbon dioxide partial pressure.
yeah, okay. Yeah, so I agree. I think it's also B there. Yeah, because if we look at A, they're saying high pH levels, but no. So high pH levels increases the oxygen affinity for hemoglobin, not the opposite. So if it was low pH values there, it would have been the correct answer would have been A. But here I'll also go with B here. So high levels of uh, carbon dioxide partial pressure, okay, will decrease the oxygen's affinity for hemoglobin. Okay, and then question 15. Okay, question 15. They're saying which one is false there? Okay. Okay, so question 15 is saying which of the following statement is false? Okay, so the first one they're saying histidine prevents oxygen from binding perpendicular to the plane of the flat tetrahedral. Okay, so this statement here, this one is true. And then B, they're saying the polypeptide chain of either hemoglobin or myoglobin prevents oxidation of iron from the ferric state to the ferrous state, which otherwise would make oxygen binding irreversible. Okay, so I think this one is not true. Anyway, let's hold. And then let's read the C. C, they're saying when oxygen binding curve shifts to the right, then oxygen is offloaded from the hemoglobin. Okay, this one is true. And then D, binding of oxygen to hemoglobin pulls proximal distal histidine and thus causes confrontational changes. Okay, yeah, so this one is true. So I think this one is the one that is false here. So B is a false statement. Okay, it's a false statement. So this one here ensures that the oxygen binding is reversible and maintains the function of the hemoglobin and myoglobin. But here you see that when saying irreversible, so this word irreversible is the one that is making this statement false. Because when you have a polypeptide chain, okay, of either myoglobin or myoglobin, okay, preventing the oxidation of whatever, that reaction there will be reversible. But here they are saying irreversible. So this statement here is false. Okay, and then question 16, they're saying which statement is false about myoglobin? Okay, so which statement do you think is false about myoglobin, according to you? Okay, so the first statement here is B. They're saying the oxygen binding curve is sigmoid. No, okay. So the one that is sigmoid is the one for hemoglobin. So for myoglobin, the oxygen binding curve is hyperbolic. Okay, is hyperbolic. So this one, this statement here is false because the binding curve is hyperbolic. Okay, due to the monomeric structure of this myoglobin. Okay, and like hemoglobin's segment. So this one here is hyperbolic. So the first structure here is B. And then 17, they're saying the Bohr effect explains what factor. How did they write this question? The Bohr effects explains what factor that affects oxygen binding to hemoglobin. Okay. So they're saying the Bohr effects explains what factor that affects oxygen binding to the what? To the hemoglobin. So the Bohr effects always talks about the pH. So the answer here is pH. So it explains the pH. Okay. Okay, so the Bohr effect, we can say it explains how changes in pH will affect the oxygen binding to the hemoglobin. Okay, so meaning that a lower pH would decrease the oxygen affinity. Okay, and then a higher pH would increase oxygen affinity. Okay, we go to question 18. Question 18, they're saying what? Okay, they're saying what bond joins one nucleotide to the next one in a nucleic acid. Okay, what bond joins one nucleotide to the next one in a nucleic acid? Okay, so the bond that does that, just a phosphodiester. Okay, so these are common questions. So phosphodiester bond will connect one nucleotide to the other in a nucleic acid. Okay, all right, and then here we've been given this diagram here for question number 19 to 22. They're saying shown below is the structure of a certain antiviral drug. Okay, it is a nucleoside analog. Okay, so meaning it resembles a nucleoside. And then they're saying use the given structure to answer question 19 up to 22. Okay, so the first question here, they're saying what nitrogenous base is in this drug? Okay, those nitrogenous bases. What nitrogenous base is in this drug? Anyone who can try. What nitrogenous base can you see in this drug? Hello?
Is it not thymine?
Thymine. No, it's not thymine.
It's cytosine.
Yes. Okay, so it's cytosine. So this nitrogenous base here is cytosine. Okay, so you pick this one as the correct one. So you should look at those two diagrams for the nitrogenous bases. You must have how cytosine looks like, you must have thymine, how uracil, all those things. Okay, those things should be in your head. Okay, and then they're saying what pentose sugar has been modified in this drug. Okay, what pentose sugar has been modified in this drug. Okay, so the pentose sugar that has been modified in this drug is the deoxyribose sugar. Okay. Okay, so the structure there, if you draw it in full, you'll see that it will lack an oxygen atom on the second carbon compared to the ribose sugar. So this here is a modified drug, okay, for this pentose sugar, which is a deoxyribose sugar. Okay, and then 21, they're saying such type of drug would be incorporated into the viruses, okay, into the viruses. So when you look at this drug here, where can it be incorporated to? Okay, so you just look at the previous question. They're saying deoxyribose. Okay, so where can it go if it has a deoxyribose? Where can it go? Definitely to the DNA, right? Okay, so this drug here can be incorporated into the DNA because it has what? Deoxyribose. If it had ribose, then it would go to the RNA. Okay. And then 22, they're saying the name of this drug is dash and is the drug of choice for treating dash. Okay, so that drug there, I'm sure it was there in your notes. Okay, so it is known as I don't know how to pronounce this word now. I don't know how to pronounce this word, but it's used to treat herpes. Okay, it's used to treat herpes, but I don't know how to pronounce that guy. Oh, no, not herpes. Ah, this one, it will be in the virus, right? So it will be used to treat this viral hepatitis. And then this word here is the one I was saying, I don't know how to pronounce it. So this question here was even there in the what? In the tutorial sheet. So we pick C there. On question number 2. Huh?
Let me read the.
What?
Let
Oh,
me
you
read
said
the.
yes. Okay, yeah, I don't know how to pronounce it, but yes. So the name of this drug is Vividin, and then it is used to treat viral hepatitis. Okay, so it was there in your tutorial sheet, this one. Usually they don't bring questions that you've never seen. Like for example, in this diagram here, it was there in the tutorial sheet. Okay. All right, and then question number 23, they're saying, what type of RNA is actually a biological catalyst? Okay, what type of RNA is actually a biological catalyst? What answer are we picking there? Is this there in the name? Okay, catalyst, it means you're talking about enzymes. Okay, so that riboenzymes there. Okay, riboenzymes are RNA molecules, okay, with catalytic activity. Okay, so they perform enzymatic functions in some of these biological reactions. Okay, so we pick D here because it is the one that acts like the biological catalyst. Okay, so question 23 is D, and then question 24, they're saying aspartame is dash. Okay, so what is aspartame? Is it an antibiotic? Is it a painkiller? Is it antioxidant, or is it a sweetener? A sweetener.
It's an antibiotic.
Are you sure? Are you sure it's an antibiotic? Okay, so aspartame is not an antibiotic. It's a sweetener. Okay, so it's a sweetener that is commonly used as a sugar substitute. Okay, so it's a sweetener. So the answer there is D. Okay, let's go to this question here. Okay, so we have been given a diagram again, and we are using it to answer question 25 to 35. 5 to 32, I mean. Okay, so they're saying below are some monosaccharides. Okay, and then they're saying use the given structures and the lectures we had in biochemistry to answer question 25 to 32. Okay, so we have D-ribose there. I can see a D-ribose. Okay, and then I can see D-glucose. I can see D-fructose. I can see D-galactose. I can also see D-mannose. Okay, so the first question there, they're saying what is the isometric relationship between galactose and mannose? Okay, so what is the relationship between those two guys? Okay, they're diastereomers. Okay, so galactose and mannose are diastereomers. Why? Because they only differ at one, they only differ at one stereocenter. Okay, they only differ at one stereocenter. Okay, is it they only differ at more than one stereocenter? Not one. Okay, they differ at more than one stereocenter, making them diastereomers. Okay, so when you look at this galactose here and this mannose, and then when we come to this stereocenter here and this stereocenter, we see that on the left here we have hydrogen, and then there we have OH. Here we have OH, hydrogen, so they differ here. Then what about here and there? We see that they're the same. Then what about here and there? We see that they differ, okay? And then here and there, they're the same. So they differ at two of these, okay? So if they differ at more than one stereocenter, okay, we call them diastereomers. So we pick 2. Okay. Hey, we pick C, I mean. Why was I saying the number? So C is the answer there, they're diastereomers. Then question 26, they're saying what type of structural representations are these monosaccharides shown in? Okay, this is just the Fisher projection, okay, because we have a straight line and then we have bonds like that. So this is a Fisher projection. So you pick B. All right, and then 27, the same. What do the vertical and horizontal bonds in each case represent? So what do these vertical lines, these ones here, represent? And then what do these horizontal lines represent? Okay, so in the Fisher projection, okay, the vertical lines, okay, are equivalent to what we call as the solid wedges, while the horizontal lines are equivalent to what we call as the dashed wedges. Okay, so simply meaning that the vertical lines represents bonds going away, okay, while the horizontal lines represent bonds that are coming towards the viewer. Okay, so remember these molecules, we are viewing them in 3D. Okay, you're not viewing them in 2D. So there will be those that will be coming towards you, and then there will be those that are going away from you. So if you have a vertical line, okay, it means that that bond is going away from you. And then if you have a horizontal line, it means that that bond is what? Coming towards you. Okay, so if something is coming towards you, we represent it by a dashed line. If something is going away from you, we represent it by a solid line. So solid line is just this, and then dashed line to be something like this. So something like this. Okay, and then for this solid line to just be something like this, and then the shade inside here. Okay, so this here solid line, it will be the vertical lines in the Fisher projection, and then this dashed line here to be the horizontal lines in the Fisher what? Projections. Okay, so we pick A there as our answer. Okay, and then question 28. Question 28. Okay, so question 28, they're saying one of the monosaccharides above is known as the sweetest substance. Okay, what is the maximum number of stereoisomers that this monosaccharide can have based on the type of projection it has been drawn in? Okay, so based on the type of projection it has been drawn in, how many what? How many stereoisomers can it have? Okay. Right, so you go here and then you identify the sweetest sugar. So which one is the sweetest sugar here? We know that it is fructose. Okay, so in that fructose, you count how many chiral centers that you have. Okay, so how many chiral centers do we have in here? Okay, so there'll be 1 here, 2, and 3. So we have 3 chiral centers here. So the number of stereoisomers will just be 2 to the power n, where 3 is the number of what? Chiral centers. So the chiral centers are 3 here. So it will be 2 to the power 3, so it will be 2 multiplied by 2 multiplied by 2, which will give us what? 8. So the number of stereoisomers based on that structure that they have drawn is just what? 8. Okay, so you use this formula 2 to the power n. Okay, so just a minute, someone is calling me. Okay, so let us continue. So I just received An important phone call. Okay, so I'll end on question 30. You come and continue from 31. Okay, so question 29 here, they're saying if the monosaccharide mentioned in question 28 above was to cyclize, okay, so meaning it becomes a ring like that. What type of ring does it usually form, and how many asymmetric carbons will it have? Okay, so as long as it's fructose, guys, okay, as long as it's fructose, the ring that it forms, okay, it's called it's called as the furan ring or the furanose ring, okay, because it's what? Fructose. Okay, so the answer there, you pick the furan ring there, okay, and then how many asymmetric carbons is it going to have? Okay, it's going to have 4. Okay, it's going to have 4 asymmetric carbons. So the answer there will just be D. Okay, so D is the correct answer there. Okay, so this furan ring is always a 5 carbon membered ring. So you have 5 carbons in the ring, and then another carbon will be outside like that. Okay, so always when you're talking about fructose, it makes that ring. Okay, and then question 30, I'll end here. I'll come and continue from 31. So which other monosaccharide on this list also forms the same type of ring as the previous question? Okay, so you go here. Which one forms a similar ring to the fructose? Okay, so the one that forms a similar ring to the fructose is the ribose. Okay, so this ribose here, it forms a similar ring to this guy. So when you come here, you pick ribose. Okay, so any questions there? Okay, maybe let me finish even 32 because we are going up to 32 with this diagram, right? Okay, so yes, you can ask your question. The one who raised the hand.
I can ask.
Yes.
Okay, so I didn't get on how you're finding how you got the 4 on the carbons. My network was tripping, so when you were explaining,
Okay, I get. All right, I get it. Okay, so here we are saying we want to cyclize, okay, or we want to form a ring using fructose. I hope you are able to get me. Okay, so we are using fructose to form a ring. Okay, so what will happen if we get this fructose and then we try to form a ring? Okay, is that this guy here, okay, this guy here will go on and react with this guy here. Okay, will react with this guy here. So meaning you lose the oxygen here and you lose the OH here. And then they will come out as water like that. Okay, so the ring will be from this guy, from this guy here up to there. Okay, so now in that 5-membered ring that you have, okay, how many chirocenters are you going to have? Okay, so remember in this straight chain like this here, we said we had how many chirocenters? Okay, we had 1, 2, 3. So when this guy here goes and bonds with the oxygen here, okay, and then a water molecule is lost like that, okay, even the guy that the bond that will be formed between this guy and this guy becomes a chirocarbon because now it will be connected to 4 different what? Groups. Okay, so that's how I'm getting the 4 here, these 4 carbons. Okay, and then 31, let's do 31 and 32. Which type of constitutional isomerism would not be possible between glucose and fructose? Okay, so which one would not be possible? Okay, so we know that between fructose and glucose, okay, functional group isomerism is there, okay, quite all right. And then this tautomerism is also there, okay. So the isomerism that cannot exist is this guy here, the furan-furan isomerism, because this glucose here, it cannot be a 5-membered ring. Okay, this glucose here, it cannot be a 5-membered ring. And then this fructose here can also not be a what? A paran ring. So this isomerism here cannot exist because this one here will have 5, this one will have 6. So glucose can have 6, quite all right, but it can't have 5. And then this fructose can have 5, but it can't have 6. Okay, so this isomerism here cannot exist. So we pick B here. Okay, and then by 32, they're saying, okay, and then 32, they're saying by treatment of mannose with this compound here, what type of modified sugar is formed? Okay, so this here is a reducing agent. Okay, that there, the sodium BH4 there is a reducing agent. So when you get mannose and then you combine it with this compound here, okay, the mannose gets reduced. Okay, so when it gets reduced, it produces what we call as mannitol, and mannitol is just a sugar alcohol. Okay, so what is reduction? Okay, what is reduction? If we remember your first semester chemistry, we said reduction is the removal of what? Hydrogen. I mean, the addition of hydrogen. Okay, so to this mannose, you add extra of these hydrogens here. Okay, and then they will be reduced to what? To mannitol. Okay, so I'll share. Someone has typed in the comment section and kindly share how the rings are developed. Okay, I'll share that. Okay. All right, so here the best answer is A. Okay, so from next time, we're going to start from question 33, and then we finish up all the 50 questions. All right, so I'll share the video when I upload it. All right, so we'll end here.